We're going to start with an example of an inconsistent system. So, do you have your graphing calculators, right? Everybody has their calculators out? Okay, first off, if I want to start by looking at the graphing calculator to graph these, in order to graph them in our graphing calculators, I have to solve each of the blue and the red equations for y, because that's how you plug it in the calculator. So how would I solve the blue one for y? What would I do? Yeah, I'd have negative y is equal to negative x plus 5. So that means y has to be positive x minus 5. Do we agree with that? Yeah. Okay, good. And then if I was going to solve the red one, I would have 3y equals 3x plus 2. So y is x plus 2/3. Do we agree with that? It's an ugly looking 3. Okay, before we begin though, there is something in those equations that gives you a hint as to the fact that this system is inconsistent. And I see it. 3 people have their hands up. If you see it, look at it. If you see it, raise your hand. There's something that points to the fact that this is an inconsistent system. Good. I want you to now tell your neighbor. What did you hear that was spreading around? Okay, all of you said that they have the same slope, but there is more to it. I think Daniel knows what it is.
Same slope with a different y-intercept.
That is absolutely correct. You see, I see the different intercept tells you something, right? If they were the same, then you'd have exactly the same line, and that would be a dependent system. All right? So, first of all, right off the bat, we have the same slope, but we have different y-intercepts. That points to an inconsistent system. Let's go ahead and graph both of those, okay? Oh, look, I already did. All right? They're up there. You can plug them in, all right? And see, if all I did was I plugged in both of those equations, x minus 5 and then x plus 2/3. And what we expected to see is exactly that. We have 2 parallel lines, so it doesn't work out. So we have looking at their slopes and their different y-intercepts. Then we have the graph that graphically represents an inconsistent system. And finally, I'm going to show you the algebraic way what you end up with. So if I'm going to use substitution here, since I've already figured out what y was, right? I'm going to take y, I'm going to plug it in right there. So that's going to give me negative 3x plus 3 times x minus 5 equals 2. So negative 3x plus 3x minus 15 is equal to 2. Well, the 3x and the minus 3x, that goes away. So I have 0x minus 15 equals 2. So you can look at it a couple of different ways. You can keep going, or you could say, well, negative 15 is equal to 2. Now, does negative 15 ever equal 2? No, not in here anyways. So what this is pointing at is you end up with a statement that is false. And if you have a false statement, that implies that your system is inconsistent. There's all kinds of things going on here, right? All right, well, let's see here. Well, let's take the same approach again, okay? If I was going to graph these things, okay, to get the blue one, I would have negative y equals negative 3x plus 7. So y would be 3x minus 7. Is that true? Did I do that right? No? Yeah, I did. Okay, good. And then the red one here, I'd have negative 3y equals negative 9x plus 21. So y would be 3x, hey, minus 7. All right. So what do we notice here? They have the same slope just like last time, but what else do they have that's the same? Yeah, in fact, those are exactly the same. Okay, so there's your first clue that these lines are just multiples of each other, right? Let's say for the sake of argument, I didn't see that. I didn't want to graph this because after all, these are the same line, so I would just see one line anyways. Let's say that I've already solved for y. I could substitute it in, right? So I would have 9x minus 3 times 3x minus 7 is 21. So I'd have 9x minus 9x plus 21 equals 21. Hey, this goes away. 21 equals 21. Now, what's the difference between this statement versus this statement. Do you guys see the difference? Yeah, one's true, one's false, right? So if we do some algebra and we do the three ways, one of the three ways, elimination or substitution, we see that we end up with a true statement. Well, that implies that we have a dependent system. All right. In order to solve, when you have a 3 by 3, and what I mean by 3 by 3 is 3 equations. You know, and I'll call this like the first one is the top one, the middle one is the middle one, and the third one's the bottom one. So I got top, middle, and bottom. When you have 3 equations and 3 variables, we call it 3 equations, 3 unknowns. It's a lot to deal with, right? 3 equations, x, y, and z, 3 variables, x, y, and z, and 3 equations. So what we need is we need a plan. And you kind of stumbled onto the plan a little bit earlier. And here's the plan in layman's terms here. So what you want to do is you want to pick an easy variable to eliminate in 2 of those equations. Okay? You want to pick an easy variable to eliminate in 2 of the equations, such as z or y or x in any of those. They're pretty easy, right? You're looking for a coefficient of 1. Once you have that, eliminate the same variable that you chose in the first one and the same variable in 2 different equations. Okay? Because if you do it in the same equation, then you're not going to get anywhere. You're going to end up right back where you started. So you want to say eliminate z in the first and second equation, then eliminate z in the second and third equation, and then you're down to what that leaves you with, step 3. That leaves you with 2 equations and 2 variables, and then just back substitute. And we're okay. So here's how we're going to do it. We're going to choose to eliminate the z. Okay? So first, we want to eliminate z from these 2 right here, from equations 1 and 2. Now, in order to eliminate z, what do I have to multiply the first equation by? I have to multiply the first equation by a 2. So I'm going to go ahead and do that and write it down here. So 2 times x is 2x. Give yourself lots of space. 2 times y is a positive 2y. You can. We're going to. Yeah. And 2 times the negative, no, sorry. You want to eliminate first, substitute later when you're getting to 2 by 2. Yeah. 2 times, where was I? Negative z is negative 2z, right? Equals 2 times negative 1 is negative 2. Did I do that right? Okay, great. Now, what I'm going to do is to keep track of this, okay, I'm going to add this one and this one together. Okay? When I do that, I'm going to create a new equation that only has 2 variables in it, namely the x and the y, because the z will be eliminated. So here we go. All right, can I do it for you? 4x and 2x, how much is that? 6x, good. Negative 3y and 2y, how much is that? Negative y. 2z minus 2z, that goes away, good. And then 16 and negative 2, how much is that? Okay, there we go. Just put a box around that and leave it alone for a second. So do you see how we now have a new equation that only has 2 variables in it, x and y? Okay, good. We're going to do that same procedure over again, except we're going to eliminate z from the first equation and the third equation. All right, now back up here. We want to eliminate the z in the top equation and the bottom equation. Okay? So how do I eliminate the z in the top and the bottom equation? What do I multiply the top equation by? Yeah, very good. Let's multiply the top equation by negative 3. I'm going to write that down over here. Negative 3 times x is negative 3x. Negative 3 times y is negative 3y. Negative 3 times negative z is a positive 3z. Negative 3 times a negative 1 is a positive 3. Did I do that right? Check my work. Thanks a lot. Equals 3. Is that good? Okay, now, again, same trick. We're going to eliminate the z from this equation and from that equation. You with me? Okay, here we go. So 2x minus 3x, how much is that? What? Negative x, good. Negative 2y and a negative 3y, how much is that? Negative 5y, good. Negative 3z and a positive 3z. Hey, that goes away, that's nice. 5 and 3, how much is that? 8. Okay, good. Now look what you have. You have an equation that has, you have 2 equations and 2 unknowns, don't you? Yeah, pretty sweet, right? You guys with me on that? So if I solve this one for y, doesn't this tell me that y has to be 6x? I don't want to mess this up for you guys. Yeah, 6x minus 14 equals y. Did I do that right? Okay, now what do I do with that? Take that, and I substitute it right there. So here's what I get. Negative x minus 5 times 6x minus 14 equals 8. So negative x minus 30x, is that right? Plus, what's 5 times 14? 50 and 20? 70? 70? Equals 8. Did I do that right? Okay, here we go. So this means I got negative 31x is equal to 70 take away 8? Negative 62. Hey, check that out. So x has to be a positive 2. Now, once you have the first one, all you got to do is back substitute all the way back up to the top, right? So if x is 2, well, let's plug it right here. What's 6 times 12? Oh, what's 6 times 2? 12. 12 minus 14? So y must be negative 2. Good. Now that I know x and y, hey, let's substitute it right back into the original one. And I'm done. X was how much? I know, it's tough. 2, right? What was x? Come on. 2. There we go. Okay. So I got 2 minus z equals negative 1. Oh my gosh, z has to be 1. There you go. So your solution set to this problem is x is 2, y was negative 2, and z was 1. And that's a system that will get you